Hey everyone! Ever wondered what's really going on under the hood of your database? Well, today we are pulling back the curtain on this. Just incredibly elegant piece of engineering that powers pretty much every database you've ever touched. We're talking about the slotted page, and it's this brilliant solution to a really tricky problem. Okay, let's get into it.
So here's how we're going to break it down. First, we're going to tackle the core conflict, the big problem that databases have to solve. Then we'll zoom out a bit to see how tables are organized at a high level. After that, we'll dive deep into the star of the show, the slotted page itself. And finally, we'll see why the simple idea behind it is just so powerful.
You know, I think the best way to picture this is to imagine a database playing a constant, high-stakes game of Tetris, right? It has to take all of your messy, different-sized pieces of data, like short usernames, long addresses, you name it, and somehow pack them perfectly into these neat, fixed-size blocks on the disk. And believe me, it is a much harder puzzle than it looks.
And that puzzle right there brings us to our first section. I like to call it the Great Translation Problem, because it's all about this fundamental disconnect between how we think about our data and how the database actually has to store it.
So here's the challenge in a nutshell. We see things as records, right? A user, a product, an order. But the database, it thinks in these rigid, fixed 8-kilobyte chunks called pages. Your username might be 50 bytes, mine might be 150. You can't just line them up like books on a shelf. The whole system would just fall apart. It's a huge engineering headache.
And, the first few solutions you might think of, they just don't cut it. Like, what if you just pack records one after another? Well, finding anything becomes painfully slow, and when you delete something, you leave these awkward, unusable holes. Okay, what if you give every record the maximum possible space? Well, you'd waste a catastrophic amount of your disk. And using a separate file as a map, that means every single lookup requires 2 slow trips to the disk. Nope. This problem needs a much more clever approach.
So before we can solve that puzzle inside the page, we actually have to zoom out and make a big architectural decision about the table's overall physical layout. And this choice, it has massive implications for performance down the line. So really, there are 2 main ways databases do this. The first is the heap model. You can think of it like a library's card catalog. The books, our records, are just placed wherever there's an open spot on the shelves, and the catalog, the index, tells you exactly where to find them. Then you have the clustered model. This is more like a dictionary. The data itself is physically sorted by its key, just like words in a dictionary are sorted alphabetically. And here's where you see the real trade-offs. Heaps, which are used by databases like PostgreSQL and Oracle, give you these super stable physical addresses, and that's a huge advantage we'll see in a minute. On the other hand, clustered tables, like you'd find in MySQL's InnoDB, are blazing fast for looking things up by their primary key, but that makes your other indexes a bit more complex. For this explainer, we're going to focus on that heap model, because it really gives us a clean way to understand the core storage concepts.
All right, and that brings us to the hero of our story. We've set the stage, we get the problem, and now here it is, the elegant, industry-standard solution that is used by pretty much every major database out there.
It's called the slotted page. And if you remember one word from this, make it indirection. That's the key. All indirection really means is that instead of pointing directly to your data, you create a stable pointer to your data. It's this one little extra step, this simple layer of separation, that is the key to solving almost all of our problems.
So check this out. This is how it's laid out. A slotted page is split into 3 main parts. At the very beginning, you have a header and a little directory of slots that grows forward. Then, at the very end of the page, you have the actual record data, all packed in tight and growing backward. And that free space in the middle? That's just the gap that shrinks as you add more and more data. It's so simple, it's beautiful.
Okay, let's zoom in on that slot array. Just think of it as the page's own little table of contents. It's nothing more than a simple list of small, fixed-size pointers, and each little pointer, or slot, tells you exactly 2 things. The offset, which is just where a record's data starts, and the length, or how long that data is. That's it.
Now, on the other side of the page, you have the data heap. This is where the real stuff lives, the actual bytes of your records, the usernames, the product descriptions, all of it. And they're packed in there tightly, growing from the end of the page backward, heading right toward that slot array. So, why do all this? Well, here's the crucial point. This whole design gives us the concept of a row ID.
A row ID is the permanent logical address for any given record. It's just a combination of the page number and the slot number, like page 8, slot 3. And here's the magic. That address will never, ever change, even if the actual data bytes get shuffled all over the place inside the page. That right there is the magic of indirection.
And here's a quick pro tip that just shows you how clever this whole design gets. Instead of storing some special character for empty or null values, records use something called a null bitmap. It's just a tiny sequence of bits where each bit represents a column. If a bit is set to 1, that column is null, and the database stores literally nothing for it. 0 bytes. It's a massive space saver.
Okay, so this brings us to our final section, where we get to see exactly why this design is so incredibly powerful in the real world. And it all comes back to that one magic trick, indirection. It gives us stability, it gives us performance, and it gives us incredible control.
Let's just walk through a scenario. Imagine you delete a record. Bam! Now you've got this ugly hole, this fragmentation, in your data heap. So to clean things up, the database can do a compaction. It just shuffles the remaining data down to fill the gap. Now, here's the aha moment. The actual data for record number 3 physically moved, but its row ID, its permanent address of page X slot 3, is still perfectly valid. All the database has to do is update that tiny offset pointer in its slot. Any external indexes pointing to that record, they don't have to change at all. It's just brilliant.
And that stability lets you pull off some incredible performance optimizations. For example, Postgres has this feature called heap-only tuples, or hot updates. Basically, if you update a record and the new version still fits on the same page, Postgres just adds the new version and points the old slot to it. You don't have to do any expensive index updates. And that one optimization alone can lead to a 7-fold improvement in I/O for certain workloads. That's huge.
Now, this leads to a really practical tool that you can actually control, called the fill factor. It lets you tell the database, hey, when you load data, intentionally leave some free space on each page. For a typical website with lots of small reads and writes, leaving maybe 10% of the page empty is a good default. And I know what you're thinking. Why on earth would you want to waste space on purpose? Well, you're leaving room for future updates. That empty space acts as a buffer, making it way more likely that an updated record can stay on the same page, which lets you take advantage of those super fast hot updates we just talked about.
And really, this gets to the absolute heart of high-performance database design. As this quote from the source material puts it perfectly, it's a fundamental principle. Sometimes you have to intentionally waste a little bit of space to buy a massive amount of performance. It is a classic space for time trade-off.
So, we've seen how the slotted page brilliantly uses this concept of indirection to solve a really complex data layout problem. But this pattern shows up all over computer science, which leaves us with a final question to chew on. Where else have you seen this same elegant trick? This idea of adding a layer of pointers to create flexibility and stability. What other complex problems does it solve? It's way more common than you might think.